Okay, everybody. So we are ready to start our part two of the section 2.5 section, section 2.5 section, where we're talking about lines and planes, and this time we're going to be talking about planes. So first thing is, what is a plane and how are we going to define it? So let's have an idea. So when we talked about lines, we didn't really talk a lot about like what a line was because you already know what lines are from earlier math classes. You knew what the equation of a line was supposed to do, like what a line is. um, but basically, if you have lines, then you can think of them just as being, they come from a point and a direction. That's how we did it in the previous section, not previous section, previous lecture. Or if you have 2 points, then there's a line that goes through those 2 points, or 2 points will determine a line. Okay. So for a plane, which is going to be an infinite, flat plane. Let me draw a plane for you. I mean, you know what a plane looks like, right? So basically, if you draw like a rectangle in space, like any kind of rectangle in space, like that, usually people understand that what we're talking about is a plane, and that this actually, extends out forever in this direction and extends out forever in this direction and in this direction. So just an infinite flat, like rectangle. So like a sheet of paper extended infinitely in all four directions. So like a plane is like a sheet of paper, extended in all four directions. Uh, say infinite size dimensions. Does that make sense? That's not a full on definition. We're gonna have a mathematical definition of this, but I think that should kind of make sense, right? So that's what a plane is. So you just take a rectangle, extend it out forever, and that is a plane in space. Okay. Now, what will it take to uniquely determine a plane? So it turns out that you would need 3 points, right? So if you have 3 points that are not on a line, so so any 3 points that do not lie on the same line, just say do not fall on the same line, will determine a plane, right? Because if you have in space, draw a little set of axes again, right? If you have in space just three different points, no matter where they are, point, 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 like that, you can connect them with a triangle, and then that triangle will lie in a plane, right? So you can extend that out in all three directions. Okay. And that's the same as extending out a rectangle in all four directions. So, three lines, 3 points will do that, determine a plane. Okay. But that's not how we do it mathematically. So the way we do this is, um, so a plane is a flat plane, right? So a plane is flat, and you can now flat. A plane is flat, and you can think of it as having a vector that points straight out of the plane. Straight out, straight out of the plane at a right angle. We call this the normal vector to the plane, or a normal vector actually. I will draw it momentarily. So normal vector to the plane. Normally we call it in for normal. So like if you've got just a flat rectangle in space like that, then you can take a point on the plane and you can draw straight out of the plane a vector, and that vector is what we call the normal vector. Okay, and so if you rotate this normal, oops, that's not what I want. If you rotate this normal vector around so it's not pointing in the same direction, then you would just move the plane around as well. So that's how we can start to get a handle of what a plane should be. Then what you can do is this. You can say, if you start with a point in the plane, so if you have a point, let's say P, let's actually give it coordinates here, x naught, y naught, z naught, that is going to be in our plane. And we know a vector that we want to be the normal vector to the plane. So I'll call the normal vector n for normal. We're going to use that till the end of the semester. So a vector n that is the normal vector to the plane. By the way, if you do anything with 3D graphics, you'll also hear normal a lot, and it means exactly the same thing that we have here. A normal in 3D graphics is going to be the direction that points straight out from the surface, or straight into the surface, but we always have, there's an outside and an inside to every 3D polygon, and the normal points outside. So that's how they determine the outside. They say whichever way it points, that's the outside. Okay, so we have a vector in that's the normal vector to the plane. So we got a plane and we got a normal vector now to the plane. So let me draw what we have. So we got plane. I don't have an equation for that. That's what we're trying to come up with now. So I've got this P. The P is x naught, y naught, z naught. And then we got the normal vector, which we know points out at a 90-degree angle there. Now, if you take any other point in the plane, so let's say, suppose the point Q, which I'll make x, y, z, no x naught, y naught, z naught, no subscript, right? So suppose Q is any other point in the plane. Right, so I could put Q here, for example, like that. Then you can form a vector from P to Q. Right, so just PQ. So where would PQ be? Well, there, right? Like that. Okay, and there's a special relationship between that vector PQ and the normal vector. Can you guess what it is? I mean, it's obvious from the picture, but maybe my picture's wrong. So what you should notice about this picture is that this line, or this vector here, which is PQ, is at a 90-degree angle from the normal vector. And the reason for that's obvious, right? By definition, the normal vector was 90-degree angle from the plane. So everything in the plane, like any line in the plane, is 90 degrees away by definition. So PQ and N are orthogonal. Okay. So what is PQ, by the way? We can actually write it. PQ is going to be x minus x naught, y minus y naught, z minus z naught, just from subtracting initial point minus, uh, sorry, terminal point minus initial point. Will give you this vector. Now, the special property of that vector is that it's orthogonal to the normal vector by definition. Um, this vector PQ should be orthogonal to n. That's why n is normal. Right? And so if PQ is orthogonal to n, that means the dot product between them should be 0. That is PQ dot n equals 0. Okay. Well, what are we going to do with that? Well, we didn't write down what the components of n were, but n is a vector, so it has an x component, a y component, and a z component. So suppose n is just going to be ABC, just some vector ABC that is given, and we know we have PQ. We found was x minus x naught, y minus y naught, z minus z naught. Then PQ dot n becomes what? So PQ is x minus x naught, y minus y naught, z minus z naught, dot n. N is just a vector for the direction, which we're just going to call ABC. And that equals 0. Or if we actually perform this dot product, you get A x minus x0 plus B y minus y0 plus C z minus z0 equals 0. Like that. And this is actually, one form of the equation of a plane. So this would be one form of the equation of the plane. Now, the reason it's the equation of the plane was the A, the B, the C were given, right? The x naught, the y naught, the z naught were given. We needed to know at the beginning here, right? I said we're given this point, and we're also given the vector n. So the P and the n were given, and this Q was just any other point in the plane. So any point Q, which is xyz, that satisfies this equation, or this equation, is actually a point on the plane. Okay? Since Q was arbitrary, xyz was any point on the plane, comma, any xyz that satisfies this equation that we just wrote is an xyz that's on the plane. Is a point on the plane. So what does that mean? So what that means is that that is the equation of the plane. So here's our definition. It gives us a definition. So given a point P and a Q, point P and vector N, the set of points Q satisfying PQ dot N equals 0 forms a plane. Okay, so this is actually already, even in this simple form, this is the equation of a plane. You don't do very much with that form of the plane, but because normally we're talking about a specific direction, but you can use that for certain things. So that's the equation of a plane, and then that's what we call the vector equation of the plane. I'll say vector form of the equation. All right. Now, if you get down and actually have numbers, right? Then if P is a specific point, which we already talked about, x naught, y naught, z naught, and N actually has components A, B, C, then this equation that we wrote up here, this is also the equation of the plane. Duplicate. Is also the equation of a plane. And by the way, you can take this and you can multiply this out, and you can move all of the constants over to the other side of the equation where that 0 is, and that's also the equation of the plane. So you can also write it this way. Write it as ax plus by plus cz equals some constant, where d is all the constants from here. So all the constants from here, right? You have like a times x naught, b times y naught. B and y naught are constant. C and z0 are constant. You move those all over to the other side of the equation, and then that's also the equation of a plane. Although they write it this way, so I'm going to write it the way they did. They left the d on this side, and the d is, if you work it out, would have to be negative ax naught, negative by naught, negative cz naught, which is a constant though. That's the key. It's a constant. Okay, and so you can write it that way as well. So this is like writing it in point slope form, kind of, when you're writing the equation of a line. So like if you know that the point, this is what you write. If you know the point and the direction, this is where you go. But if somebody's giving you like a simple looking plane, they probably write it like this. So there's just multiple ways to write the equation. You'll see both. Okay. So how would we actually use this stuff to come up with the equation of a plane? Let's try. Let's see. Oh, also, I guess they call this general form. So if you're looking for a general form of the equation of a plane, I guess that's what they want. Which, by the way, it's a little bit weird that your book does this. A lot of books move the D over to the other side. Don't know why yours doesn't, but it doesn't. Okay, let's do a problem. So let's see, find the equation of the plane containing, and we're going to go 3 points. So our points are 1, 1, negative 2. Q equals 0 to 1. And R is negative 1, negative 1, 0. Okay. How would we do it? So here's the idea. So you've got a plane. Your P, your Q, and your R are all in the plane, right? So P, Q, and R, right? So P, Q, and R are in the plane. Now, what do you need in order to write this equation, though? You need, given a point P, okay, so we've got 3 points. So we only need 1 point in the plane. We've got 3. That's fine. So we're covered there. But the other thing you need is not a point in the plane. You need a vector, right? You need a vector that's supposed to point straight up from the plane. Where are you going to get a vector that points straight up from the plane? So you have to think about it. So we need the normal. So what are you going to do is you need to make some vectors. So make vectors. Let's say you don't have, it doesn't matter which way you do it, but like, let's say I do PQ and PR. You just need any 2 vectors in the plane. So you just make a vector there and you make a vector there. PQ, PR, right? So you make those vectors. Now those vectors are in the plane. They are in the plane. So what do we need? We need a vector that's 90 degrees away from those vectors. Orthogonal to both of those. We need a vector orthogonal to both. How do you do that? So you have to think, how do you form or how do you find a vector that's orthogonal to 2 other vectors? And think back to the previous 2 lectures. We learned how to do that, right? That's what a cross product does. That's what a cross product does. So we say that's what a cross product does. Right? So what you do is you do this. We compute that the n is going to be PQ cross PR. Now, again, it doesn't matter which vectors you have in the plane. You just need any 2. So it doesn't have to be PQ. You could do like PQ and then RQ or something, RQ or whatever. If you have like 5 points, it doesn't matter which 2 you use for either one. So just 2 vectors in the plane. So we get this normal like that, and we're going to calculate it. Needs to be orthogonal to both, and that means what we do is we take a cross product. All right, so let's do it. So what's PQ and what's PR? Can I see this? Yes, I can. All right, so PQ is going to be the vector what? So you can't see it. Or I'll just drag these down. Hold on. Duplicate. Move them down. I'm just going to bring them down here and then I'm going to erase them in a minute. Or just move them somewhere else. Okay, so PQ. So that would be 0, minus 1, 2, minus 1, 1 minus minus 2. So we get -1, +1, 3. Will that work? Think that will work. And then we need another vector, which we said we're going to use PR. So let's use PR. So that would be -1 minus 1. -1 minus 1. Wait, yeah, that's right. And then 0 minus minus 2. So we get what do we get? So -1 minus 1 is -2. -2, +2, I guess. Hopefully I did that right. I guess we'll find out. Hopefully I subtracted correctly there. I feel like I didn't for some reason. Okay, so you find those. Now that you have those, you need to actually do the cross product in order to get the normal vector. So the normal vector is going to be the cross product of -1, 1, 3, and -2, -2, +2. So we know how to do that. IJK, -1, 1, 3, -2, -2, 2. This is where, at some point you start to get tired of doing these. As long as you're comfortable doing them, then, you can use Wolfram Alpha and sites like that to help you get the answer a little bit faster here, rather than, taking forever just to do cross products for no reason. We have I 1, 3, -2, 2 minus J -1, 3, -2, 2, and then plus K -1, 1, -2, -2. Okay, so what do we got? So we have I here, and then we got 2 plus 6, so that's going to be 8. And then I've got minus J, parentheses. We got -2 plus 6. -2 plus 6 is 4. And then plus K, +2 minus minus 2. So that's +2 plus 2. So that's 4. So overall, what do we get for this vector? I don't like this form. So we get 8, -4, +4. That's our normal vector. Okay, so we got our normal vector. At this point, we now have a point and we have a normal vector. So all we need to do is use them now. A normal vector n equals 8, -4, 4. And we have a point. We actually have 3. It doesn't matter which one you use. I'm just going to use P. What was P? 1, 1 minus 2. And that's enough to write the equation of a plane. All right, so how do we do that? Well, we're going to go back to our definition of the plane. And so we had A x minus x naught. This is the form that we want, plus B x minus x naught, plus C, wait, try again, y minus y naught, plus C z minus z naught equals 0. So that's the form of the equation that we're going to use. And I just want to mention that up here. Scroll up. Okay. So this is the one that you can plug the numbers in directly. You can't really plug the numbers in directly here because, well, you can plug the ABC, which is your in, but where does the point go? X0, Y0, Z0. You don't see it in this form. So you don't really generally use this for writing the equation of a plane from scratch. You could, but it's a little bit tedious to do that. This is the more convenient form for writing the equation of a plane. So you just write it out like we just did, and then you substitute your p and your n, and just make sure you understand which one's which, right? The n is the ABC, and the p is the x0, y0, z0. So you just plug all the numbers in the right place. So we get 8 x minus 1 plus, actually minus 4, parentheses, y minus y0, which is 1, plus c, which is positive 4, z minus z0, z0 is negative 2. Like that. So this is one form of the equation. So this was the general form, I guess. Um, no, it's not. It's just the equation of a plane. Usually what you do is you will simplify it. So let's rewrite it. Let's say ax plus by plus cz, I guess, minus d equals 0 form. Okay, so how would you deal with that? Well, you just multiply it out. So just multiply out. So you have like 8x minus 8. When you multiply this, then you got minus 4y plus 4 for the middle one. And then for the z term, you've got 4z plus 8 equals 0. And then you basically take the 8x, not basically, minus 4y plus 4z, and then add up the other constant. So you got your negative 8 plus 4 plus 8, and overall that adds up to 4. So then this is the equation of the plane as they want it, I guess. So that's your general form. Okay. So that's how you come up with the equation of a plane. And so you can see that what we did was, uh, because we were given 3 different points, we had to calculate the normal vector. And that's really where all the work was, right? Like everything that's on the page here was computing the normal vector, and that's where all the work was. So if they just give you the normal vector, then most of this work is not needed, right? None of this work is. You can just jump straight to this if you're given the normal vector. So like what we just did was like the longest version of finding the equation of a plane. Okay, maybe let's go back to GeoGebra here. Let's see if we can figure out how to plot a plane. I don't know. Let's delete a couple of these. Delete, delete. All right. So we got one of these up here. How do I? Come on, please just let me scroll. Okay, there we go. Stop. This site is not the best for navigating with big fat fingers. Okay, so let's call her A 1, 1, negative 2. I don't know if I'm actually going to be able to plot this, but I'm going to try. B is going to be, I guess, what Q was, 0, 2, 1. Let's do a C. I'm just keeping ABC just because that's what it was typed in already. Negative 1, negative 1, 0. Negative 1, negative 1, 0. Okay. Okay, so we got 3 points here. right? And then they're in space, and you can see that, there should be a plane that goes through them. Maybe we can figure out how to do it in GeoGebra here. So let's tools, I guess. Oh, let's do this. Planes. Plane through 3 points. Excellent. So plane through 3 points. So if I press that, then I should be able to select my 3 points, right? A, B, C. Oops. And then I just got a D just because I kept pressing stuff. Right, let's go here. Oh, tools. Tools. Okay, algebra. Let me go back here. What is this? Delete. Okay, cool. Tools, algebra. Excellent. So they wrote the plane this way. You can see, I can't make that big, but you can see hopefully on this last thing I did on GeoGebra here, where it says plane, plane ABC, and it's 2x minus y plus z equals -1. And that's actually, that should be what we calculated over here as well. Because if you take this right here, if you just divided everything by 4, right? Because you can just notice all the numbers go through 4. Divide by 4, and you get 2x minus y plus z plus 1 equals 0. And then if you move the 1 over, you get 2x minus y plus z equals -1. So this is the form that they gave you from GeoGebra. But you can see that wasn't that hard. The way to do it was to type in those 3 points and then go to the tools. And then when you go to tools, that's where they will, in the tools menu, you can find where to construct a plane through 3 points. Now, if I click plane, like I don't know I don't know how to do plane without 3 points. So maybe I would have to have a vector and a plane, but I don't know how to construct a vector in GeoGebra either at the moment. So anyway, we at least did something. We calculated a plane on GeoGebra. Okay, so let's do a different type of problem. Let's just pick a problem. This is the next example in the book. They say, oh, okay, that's interesting. Find an equation of a plane, I guess the plane, but I'll just say a plane, through the point 1, 4, 3, that's a point, that contains the line x equals y minus 1 over 2 equals z plus 1. So this initially, like, they're just giving you confusing information. And so what you want to do is, first of all, understand what information they're giving you. So there's supposed to be a plane, right? Because we're supposed to find the equation of it. So there better be a plane. And there's a line, right? There's a line that contains this. Now, I don't know where that line is or anything. I'm not drawing this exactly. I don't care what this line looks like. It's just a line. So just put this line somewhere. So just say, okay, well, the line is there in the plane. Okay. Now also the plane contains this point 1, 4, 3. So this point 1, 4, 3 is in the plane. Okay. So that's great. We got a point in the plane. So like before, we need to figure out where we're going to get a normal vector from, right? So that's like figure out what they're giving you, kind of draw a picture to see what it is, and then we can figure out what we're missing, right? We see we have a point. I'll call it P. P143. We're missing the normal vector. Okay, so we don't have the normal vector. So where are we going to get a normal vector? Uh, probably you can imagine that we're going to do some kind of cross product again. And there's a lot of different ways we can do this. So what's one of them? So we're missing the normal vector in. We're probably getting it from a cross product. This is how you're supposed to be thinking when you're solving these. So we probably get it with a cross product. Okay, great. Cross product of what? Well, if we are going to use a cross product, we need two vectors that are in the plane. Then we can do a cross product to get the normal vector, orthogonal vector. Okay, so this is what you should think. So we need two vectors in the plane. So one of the vectors, you don't have to, but one place to get a vector would be from the direction vector of the line. That's one place to get one. You don't have to get it from there, by the way, because you could also you could skip that, forget all about it, say we don't even need to know, like we don't know anything about lines, and just say like, okay, if we don't want to use that direction vector, you could also figure out 2 points on the line. And if you figured out 2 points on the line, now you've got 3 points. And once you have 3 points, you can solve it exactly the way we did this one up here, right? Once you have 3 points on the plane, then you can form two vectors and then do the normal. So you don't have to use the direction vector of the line in order to get one of those two vectors, but you can, and it's an option. Okay, so our choices are those. So let's see. We could get one vector from the direction vector of the line. Okay, do you remember how to do that from the previous lecture? So remember it was like this, like x minus x naught over a, x minus y naught, no, y minus y naught over b, z minus z naught over c has direction. The direction vector was the ABC, right? So we could do that. So you can just observe this line here and figure out the direction vector. The direction vector is the denominators of each of these three fractions, right? We did that once in the previous lecture. So let's do it. So for the given line, the direction vector is the denominators up here. So the denominator, you don't see it. So it's 1, 2, 1, right? Because there's no denominator. So 1, 2, 1. That's one place we can get a vector in the plane. 1, 2, 1. Okay. So for the other one, we're going to have to find, we're going to have to figure out a point on the line and then find the vector from the point to the point. For another vector in the plane, we'll figure out a point on the line. I'll call it point Q on the line. The name doesn't matter. And then find the vector PQ, right, where P was given. All right, so how do we find a point on the line? In order to find a point on the line, find any x, y, z that satisfies the equation of the line. So where is the equation of the line? Let's copy paste it. It's right here. Duplicate it, drag it down. All right. So any x, y, z that satisfies that. So the easiest one is going to be whatever makes each of these 0, right? So take the x, y, z that makes all 3 of those 0. So, all right. So for example, 0 makes this 0, 1 makes this 0, -1 makes this 0. That's the easiest one to get. Basically, you're looking at this and you're reading off the x0, y0, z0. So what makes this 0, what makes this 0, what makes this 0? And you get 0, 1, -1. Okay, so we've got Q is on the line. Once you have the Q that's on the line, then you can find the vector PQ. Let's can't do that until I remember what P is. So I find it up here. This was given. So what's the vector PQ? We subtract. So we get 0 minus 1, 1 minus 4, -1 minus 3, for the vector -1, -3, -4. Okay. You could also take the opposite direction there and do +1, +3, +4. Or so like we could do this one instead. Doesn't matter. I'll probably use that one just because it's less negatives to write. Okay, so at this point we've got 2 vectors. Now we have 2 vectors and can find n, the normal vector. So n is going to be, what are we going to do? We're going to have to take the cross product between the PQ, or actually I'm going to use QP because of the negatives, cross V, I think I called it V. Yeah, V, which was 1, 2, 1. So what we need is 1, 3, 4 cross 1, 2, 1. All right. Again, this is where, maybe you want to use Wolfram Alpha because you're lazy. Actually, maybe I will, just because you see me calculating everything by hand. And if I was doing this myself, well, actually, if I was doing it myself, I probably would just calculate it by hand. But just remember, you can always go cross and then just type in your vectors like in parentheses here. 1, 3, 4, parentheses, comma, parentheses, 1, 2, 1, parentheses, parentheses. You can verify that it computed the right thing. Right, so this is actually how, like, if I was doing a lot of homework, I would do this. Because I know that I know how to do cross products, and I'm not worried about, like, forgetting how to do that, so I don't need to practice. So use Wolfram Alpha. Okay. So, skip the work for anybody looking just at the notes later. So I skipped the work, we did that cross product. Once you do the cross product, then we can go to our equation of the plane. A x minus x naught, b x minus x naught. I keep doing that. y minus y naught, c, z minus z naught. I don't do it with z, only with y. Okay, so the plane is that, and we fill in everything. So the normal vector is the ABC. So I'm going to have the 5, 3, oh, it's -5. -5, 3, -1. And then we can use any point that we want, but you know, this is one of them and this is one of them. So those are, oh, you can't see what I'm circling. This is one of them and this is one of them. So whichever one, you know, you feel like writing. Oops. So whichever one. So I'll drag that down so I can see it. 1, 4, 3. So this was the given point. Oh, come on. Right. Man. All right. So we did it. That's the equation of the plane. Now you can multiply that all out, of course, and simplify this, which I guess we will, just because. What will we get? -5x plus 5 plus 3y minus 12 minus z plus 3 equals 0. So you got your, collect your x, y, z. So -5x plus 3y minus z. And then add up all the constants. 5, -12. So we're at -7. -7 plus 3 is -4, right? Okay. And that would be the general form of the plane. Okay, so yeah, so we wrote the equations of some planes. I think there's one thing, two things that we have left to do, three things. Oh, you're killing me. Four things? Oh no, we're 52 minutes in. We still got lots left to do. You know what time it is? It's 1:15 in the morning. My neighbors are probably tired of listening to me. Oh well. Okay, so where were we? Distance between a point and a plane. Okay. So distance distance between a point and a plane. Okay, so let's think about this. We thought about, I mean, we did a distance between a point and a line before. You might think this is harder, but I don't think it is. So let's see. So you got a plane, which again, we generally draw just sort of as a rectangle, and everybody understands that it extends in any direction. And then you've got this point that we care about that's not in the plane. Okay, so I think the point that's not in the plane is going to be over here, P. Okay, so how does this work? So I think that the idea is this. So we've got this P that's just in space, not in the plane. Okay, now Q is going to be any point in the plane. Okay, so Q is here, just somewhere in the plane. Okay, now the thing is that every plane has a normal vector, right? So every plane has a normal vector. You can read them off of the equation. We haven't had to do that yet, but you know, you can look back up here at this And if you think about where it came from, you would know that the normal vector to the plane was -5, +3, -1, right? Just the coefficients on the x, y, z. That's the normal vector. So every plane has a normal vector that you can find. In. So I'm going to draw the in. You can draw it anywhere on the plane. I'm going to draw it coming straight out of the point Q. Doesn't need to, but I'm going to draw it there. Draw it big. Okay, so that is in. Okay, now the thing is that, of course, just like on the previous problem, you know that the issue is that you can figure out the distance here between the P and the Q, but the distance between P and Q is not actually the distance between the point and the plane, right? That distance that I just drew is too long. The actual distance you need is this, oops. Come on. The actual distance you need is this distance, right? And it was a little bit of work to figure out what that distance was going to be in the previous section. But for the distance between a point and a plane, it's actually very easy conceptually, because if you draw the vector p to q, oops, if you draw the vector p to q, or qp, it doesn't matter. I guess I'll draw q to p, vector q to p. You see that that's not the vector of the right length, not the shortest distance from the p to q, from p to the plane. So that's not the shortest vector from p to the plane. But what you can do is, if you take this vector and you project it onto n, remember vector projections, if you simply project this onto n, you're going to find this vector. And that vector is actually the same length as that, like this vector is the same length as this vector, which means this vector is actually the right length. So you just do the projection of QP onto n, and that's the vector of the right length, or the magnitude of that vector is what we want. So turns out from the picture here, we see that the actual distance from P to the plane is, I'm going to use a D for distance. It's the magnitude of the projection of QP onto N, or that's, there's a formula for it, which was, oops, you could say it's the absolute value of the component, right? Remember that there were two types of projections, scalar and vector. So the magnitude of the vector projection, or the absolute value of the scalar projection, or what we're actually going to calculate, which is qp dot n, absolute value over the magnitude of n. So that's actually like pretty easy to calculate. Okay, so this is that's the formula that you use. Oh man, I'm seeing that the color looks really light on my desktop. Hopefully you can read that. Okay. So I'm not going to write like theorem, blah, blah, blah. Well, I will actually. Theorem. But I'm not going to rewrite that whole thing. So that's the distance from a point to a plane. So it actually turns out to be easier than you think. It turns out that it's just a dot product and a magnitude when you work it out. And it's just from that picture where the vector projection is the right length thing. So no complicated trig or anything like that. Okay, example. Let's do an example. Um, find the distance from point P, which is 312, and the plane given by x minus 2y plus z equals 5. Okay, now again, that sounds like a hard problem. It's not a hard problem because we just need to identify, we just need a q that's in the plane, and then we need the normal vector and so on. Okay, so, for the distance formula, we need, what do we need? So just looking at the formula, we need QP and N, right? Okay, that's what we need to get started. We have N. From the plane's equation. Right, so you need, this is a tool you need. So you're just reading off the coefficients of x, y, z. So the coefficients are 1, -2, +1. Okay, so we have the N, that's easy. We also have the P, we need the Q. So the P is 312. We need Q. Now what's Q? So remember, what did we say? Q is any point in the plane. Any point in the plane. So how do you find any point in the plane? And again, this is something that we haven't had to do yet. So we need Q. Any point in the plane. So what you do is a plane is an equation with 3 variables in it, right? So what you do is you just pick 2 of them yourself and then calculate the third. So the easiest way is just, so you just take the equation of the plane, which somewhere, x minus 2y plus z equals 5, 3 variables in there. So you just pick 2 of the variables to be whatever you want them to be and calculate the third. 2 variables to be whatever you want. And calculate the third. It's super easy, right? So like, for example, you can just say Q. Like, let's just put a 0 for x and a 0 for y. 0, 0, what? Right? So if you just put a 0 for x and for y, you would have 0 minus 2 times 0 plus z equals 5. Z equals 5. So that works. 0, 0, 5 is in the plane. But you didn't have to do that. You could have put, you could have put 0 for y and 0 for z, or 0 for x and z, or you could have put 1 and 1, or anything you want, right? Or like if you put in a 1 and a 1, what would you get? You'd get 1 minus 2 times 1 plus z equals 5. So you have 1 minus 2, which is -1 plus z equals 5. So z equals 6. Right? Right. So it's actually super easy to find points in the plane. So as long as you understand what the equation of a plane means, right, which is that any x, y, z that satisfies the equation of the plane is a point that's in the plane. So it's really easy to get points in the plane, just whatever you want. So let's just use the first one. So we'll use the P was given to be 312. And Q, we could use lots of them. Let's just use 005, right? I like zeros. If we wanted more zeros, we could have used 3 and 1, by the way. We could have used 3 and 1 for X and Y and then calculated the Z. And then when we did the subtraction, maybe it would have come up more favorably, but whatever. We didn't. All right, so what are we supposed to find? We're supposed to find QP. And then QP is, QP, not PQ. Oh, well, I mean, it doesn't matter. Okay, QP. So 0 minus 3 for the X components, 0 minus 1 for the Y components, 5 minus 2 for the Z components, or -3, -1, +3. Okay. So now we've got our Q, P, and our N. So finally, we can compute the distance. The distance was absolute value QP dot N over the magnitude of N. So let's just put in everything. So we got absolute value QP is -3, -1, 3 dot N. N was somewhere 1, -2, 1. Wait, 1, -2, 1. And then in the denominator, we have the magnitude of 1, -2, 1. Okay, so let's calculate that. So numerator, we're just doing a dot product. Dot products are easy. -3 times 1 is -3. -1 times -2 is +2. 3 times 1 is 3. Denominator, we got square root of 1 squared, 2 squared, 1 squared. So what do we get? Looks like 2 over square root 6, I guess. Which again, we don't typically bother rationalizing denominators in this class. But this is also around 0.82. Okay. So that was the distance between a point and a plane. And most of the work is just coming up with the numbers that you need. Well, I mean, I guess, yeah. Okay. Okay. 2 simple topics left. All right. We can do it. We're 1 hour and 8 minutes in. This is a long lecture too. Why are they all long lectures? Is it because I'm slow? Okay. Parallel and intersecting planes. Okay. So, obviously parallel planes, they're going to have, they don't intersect. And the way that they don't intersect is that they're going to have the same, they're going to have parallel normal vectors. So they have parallel normal vectors and no points in common. Right? So like plane up here, plane down here. And if you look at the normal vectors point in the same direction. They don't have to be the same length. One can point down and one can point up. None of that stuff matters. But the planes are tilted in the same direction. So that's what parallel planes do. Intersecting planes So if they're not parallel, then they do intersect. And they specifically intersect in a line. So easiest way to draw this is to draw the line first. So like if I draw, come on, straight line. Okay. So if you have a line like this, right? So like imagine that you got a plane like this, and that line like is actually like hold on, right? Like the line is actually on the plane. Okay. Now if you have a plane that is not parallel to that plane, maybe it will intersect. So what does that look like? Right? So something like that. So anytime that planes are tilted with respect to each other like this, then the intersection point is going to be a line like that. Okay, so I think from the picture you can see what I'm talking about, that they intersect in a line. And one common problem is they will give you two planes and they will say, find the equation of the line of intersection. So that's a little bit weird to do. I actually don't like the way that they do it, but actually, let me think for a second here. Do I want to solve it the way that the book solves it, or do I want to solve it a different way? Um, yeah. Okay. So a common problem is to give you two planes and make you come up with the equation of the line where they intersect. Okay. There are multiple ways to come up with that line. I'll show you one. And the book does a different one. Okay. So what do that look like? So how would we do that? So they give you two equations. So they say, um, you know, given x plus y plus z equals 0, and another plane, 2x minus y plus z equals 0. Those are two planes. Uh, find the line, or sorry, I'll say find, I'll say parametric equations of the line of intersection. Okay, so here's a fact. So this is not the solution that they do in the book, but this is how I'm going to do it. Fact. So just look at the picture of the intersection. Now, the line here in this picture, right? The red line that I drew here, it's in the purple plane, right? The line is in the purple plane, and also the line is in the blue plane, right? So the line of intersection is in both planes. Okay, so that's a fact. The line of intersection is in both planes. That's why it intersects both planes. Okay, now Um, that means that it's orthogonal, like any line in a plane, right? Going way back up to the beginning of planes, um, way back up. Everything in the plane is orthogonal to the normal vector, right? So the line of intersection is orthogonal to the normal vector. Which normal vector? There's two planes. Well, it's got to be both. Okay, so the line of intersection is in both planes. So it's orthogonal to the normal vectors of both planes. Does that make sense? Right? Like if you drew the normal vector, oh man, it's hard to do. Um, but like the normal vector of the purple here would be like this or something, right? And that's going to be a right angle. And the normal vector of the blue plane is like, I don't know, it gets straight up. And this is also a right angle. So it has to, the intersection actually has to be normal or perpendicular to both of the normal vectors. So it's like like it's a third thing that's orthogonal to the other two. So line of intersection is in both planes, so it's orthogonal to the normal vectors of both planes. Right? That means its direction. So you can get the direction vector of the line from the cross product of the normal vectors of the planes. Okay, so that's first. So we can get that way. So for the two planes that we have, so for what were our equations of planes? X plus y plus z equals 0, and 2x minus y plus z equals 0, right? So there's two normal lines, two normal vectors to those planes. The normals are, I'll just call them n1 and n2. So for the first one, it's 1, 1, 1, right? We're just reading the coefficients, remember? And for the second one, n2, just for the second normal, we read the coefficients 2, -1, +1, 2, -1, +1. Okay? So the direction for the intersection you can get with the cross product. So get the direction v with a cross product. So we have to do 1, 1, 1 cross 2, -1, 1. And again, I could do this by hand. It's late. I'm tired. The lecture's long. You want to stop watching. I want to stop talking. Cross product. Wolfram alpha. Do it. All right. So what we got? 1, 1, 1. 1, 1, 1. 2, -1, 1. Parentheses, parentheses. Go. All right. So we get our cross product. We got 2, 1, -3. Awesome. Okay. So we have the direction for the line. So what do you need for the equation of a line? You need a direction and you need a point. all we need is a point that is on the intersection of the planes. Right? So we got, like, on our picture here, we now know the direction, right? That's what we just called V. But what we don't know is a point. So we need a point that's there. So how would we get that? A point that's on the intersection. So we need a point that's on both planes. So how could we get that? The easiest way to get a point that's on both planes is going to be how we just got a point for that was on a plane previously, right? How did we get a point on a plane in the previous problem, right? We said we could do this. We could choose two variables to be whatever we want, and then you can calculate the third, right? Um, Wait, will that work? No, because it's got to be the same point that's on both. Oh no. Okay, so we can't do that. So it's a little bit more complicated. So we need a point that's on both on the intersection of both planes. So let's get those equations for the planes. What are they? X plus y plus z equals 0. And what? What's the other one? Sorry, looking for it. Okay, 2x minus y plus z equals 0. So here's what you're going to do to get a point that satisfies both equations. So first of all, there's two equations to satisfy, right? And you know that if you have two equations and two unknowns, that's the way to that you can solve that. Okay, so there's like a shortcut. So I'll tell you the shortcut first. Actually, so shortcut. You can just look at these and notice that 0, 0, 0 is a point that's on both planes. Okay, but normally that's not going to be the case. Like, it's not going to be that easy. So we're not going to do it that way. So let's not use that. Too easy, right? We want to be here forever. So here's what you could do. So just in general, where you can't make it that easy, what you do is just choose one of the variables. Choose a value for one variable. Like anything. Example, right? We're going to choose, like, let's say I just choose x equals 0. No, you know what? I don't want 0, 0, 0. Let's pick a different one. But you could. So choose a value for one variable, anything. So I'm just going to choose x equals 1. Okay. Now the equations become what? So you put in x equals 1. So the equations become 1 plus y plus z equals 0. And the other one is now 2 minus y plus z equals 0. Right? Now what you want to do is solve these for y and z. So solve for y and z using any method. So for example, I can simply take them, like if I call the first one 1 plus y plus z equals 0, and I call the second one 2 minus y plus z equals 0. So if I call them 1 and 2, right? 1 minus 2, actually we can just add them. 1 plus 2, just add these equations, and you would get 1 and 2 is 3, plus y plus minus y is 0, plus z is 2z, equals 0 plus 0 is 0, right? So I get, what do I get? 3 plus 2z equals 0. We got to solve this for z. So we get 2z equals negative 3. Z is negative 3 halves. Okay, so we got that. Z is negative 3 halves. We already had x equals 1. Then we're going to substitute that z equals 3 halves back into one of the equations. Into 1 or 2, doesn't matter. I'll choose 1. So we have 1 plus y plus negative 3 halves equals 0. So that's y minus a half equals 0. So that's y equals a half. Right? I think. So I've got the xyz. So if we take the xyz together, that would be x was 1 because I said so, y was 1/2 because I found it, z was negative 3 halves because I found it. Okay, and so that method will always get you a point that should satisfy both of those equations there. Okay, you can double check that it also satisfies equation 2. I think it must. Negative y is negative 1/2. Yeah, okay, good. All right, so you do that, so you got a point. Okay, now once you have that point, we've got what we need because now we have a direction vector and we have a point. So finally, we have a direction. V was, what was it? 2, 1, negative 3. And a point, which was, wasn't called P, right? It was called Q. Was it called Q? I don't know if we called it anything. I don't know. I'm just going to erase the Q. 1 positive 1/2, negative 3 halves. Or 0, 0, 0 if we were smarter, right? Okay, so we got a point and a direction. And if you have a point and a direction, you can write the equation of a line. So the equation of the line of intersection between those two planes, that's what we were doing. If you forgot, this is what we're doing. So, right, planes, or sorry, lines look like this. And then you put your point, 1, 1/2, negative 3 halves, plus, plus, plus. And then you put your direction vector, 2, 1, negative 3, and parameter t. Okay? And that would be one way to write the equation of the lines. Now, first of all, remember, like back up here, I said that you could just notice that 0, 0, 0 was on both planes. If you did notice that, you would have skipped all of this work and you would have just had this is 0, 0, 0. So this would have just been 0, 0, 0 here. And 2t, 1t, negative 3t. And that's the book's answer because the book didn't use this point. Now, I made that longer than it needed to be by, not noticing that 0, 0, 0 was on the plane. But I still think that my method's easier to understand than what the book did. So, if Newton Alta shows you a different method, you can use it, but I would recommend this. All right. Okay. So I think, man, this is so hard. Okay. It's not hard. It's just I'm annoyed with how long this is taking. All right, so let's do the angle between two planes. So angle between planes. So if you do have two planes, I'm gonna draw them like this. Okay. So it turns out that it's actually very simple. Um, it turns out that the angle between two planes, right, that are not parallel, uh, is simply just the angle between their normal vectors. Okay. And you can probably see that, or at least think about it, right? Like if there's an angle between these planes here, right, theta, then also if you put the N1 and the N2 right next to each other, that'd be the same theta. Um, just because if the planes were overlapping, right, then they would both have the planes would be on top of each other and both normals would be sticking straight up. And then as you move the plane this way, the plane moves at the same time as normal vector is moving. So start with parallel planes and parallel normal vectors, and then if you rotate the plane 30 degrees, you also rotate the normal vector 30 degrees. So everything matches always, right? So it turns out that the angle between two planes is simply the angle between the normal vectors in1 and in2. So how would you calculate it? You just use the formula for the angle between two um, two vectors. So to compute the angle between planes with normal vectors in 1 and in 2, um, you use this formula, cosine theta, and so it's the dot product of the normal vectors over the magnitude of the normal vectors. And that's just the normal, like this is just the definition from when we learned about vectors and the angle between vectors. So very, very simple. Okay, so you can use that. I don't even think I'm going to do an example of that for time purposes. What else can we do? Okay, so this is the last thing, I think. I hope. Okay, so I'm not going to prove this. So this is going to be the distance between a point. Uh, wait, to a plane. Did we do the distance between a point and a plane already? Wait, yeah, it was a projection, right? Okay, I'm not crazy. Okay, so they give this theorem. So let P be x0, y0, z0. That's a point. Be a point. And We don't have it. We don't. I don't need a name for the plane. We also have a plane, an unnamed plane, ax plus by plus cz plus k equals 0. Why k? Because they want to use d for something else. The distance from P to the plane is D equals A x naught plus B y naught plus C z naught plus K over square root A squared plus B squared plus C squared. Okay, now where does that come from? Well, this comes from the other formula that we already saw. So this comes from D equals QP dot n over in magnitude that we saw earlier. This was absolute value. Okay. So like you can see the stuff that's associated. So on the bottom, it's the magnitude of n. This is the magnitude of n. On the top, this is supposed to be a dot product of the normal vector, which is ABC. So you see that here, ABC. And a point that's on the plane, or sorry, a vector from P to Q, where Q is on the plane. And so what they did is they came up with the Q, a specific Q. They did the dot product, and this is the result. So this isn't really a different equation. It's just kind of like an example of using this. Okay, but this is kind of a shortcut for finding the distance between a plane and a point. Okay, so I'm just going to use that formula when we need it. And then I'm going to have an example here of something else. So here's something we haven't done. So find the distance between the two parallel planes. Uh, 2x plus y minus z equals 2. And 2x plus y minus z equals 8. Okay, so so the thing is that I didn't give you a formula for the distance between parallel planes, right? So when you think about this problem, that's the first thing you should think of is, number one, we weren't given a formula for the distance between two parallel planes. Okay, but here's the second thing you should think. So we don't have a formula for it, but we were given the formula for the distance between a point and a plane. Right? So what you do is, you bust out the big brain and you think, okay, well, I don't know distance from plane to plane, but I do know distance from point to plane. So I got two planes. So what you do is you just pick a point on the first plane, any point on the first plane, and then measure the distance from the point to the second plane, right? So we don't know how to do two planes, but we do know how to do point to plane. So you just come up with a point first and then do that. So what you do is, so find a point in plane one, plane number one, then find distance from the point to plane number two. And the reason that works is because if you have parallel planes, right? So they're not touching. So if you find any point, right, no matter what, any point in the top plane, the distance from there to here is the same, right? Like if this distance is 5, this distance is 5, this distance is 5, right? The distance from any of the points in the top plane to the bottom plane are equal. So they're all the same distance because the planes are an equal distance apart. So it doesn't matter what point you use is the key. Okay. So having described the process, here's what you would do. So we got plane one, right? Here's plane one. So let's do this. So find one point in the plane. How do you find a point in the plane? Remember how we said to do it? You simply pick two of the values and calculate the third. So whichever ones are easy. So let's use 0 and what, right? So if you plug in a 0 for x and a 0 for y, you get 0 plus 0 minus z equals 2. So you get z is minus 2, right? So there's your point, okay? So now we have a point. So now you find the distance from point 0, 0, minus 2, which is in the first plane, to the plane, whatever the second plane was. The second plane was 2x plus y minus z equals 8. Okay, find the distance from the point to the plane. So then that's where we use the formula. And now we want to use this formula. D equals, it was ax naught plus b y naught plus c z naught plus k over magnitude a squared plus b squared plus c squared. And this is assuming, right, make sure we know what everything is. So ABC is the normal to the plane. Okay. And x naught, y naught, z naught, what's that? X naught, y naught, z naught was the point. I wrote it as a vector here. Is the point in question. And what's the equation of the plane? And the entire equation of the plane was ax plus by plus cz plus k equals 0. Okay, so we know what everything is, right? So like if we label everything up here, then this is x naught, y naught, z naught. And this is a, and this is b, and this is c, and this is not quite k. Because we have to move this over to get k. K if we move it over. So k is actually negative 8. Because it has to match this. Okay, so having said that, we just substitute all of the numbers in to the formula. We get d equals absolute value. A is 2, x naught is 0. B is 1, right? We're reading them off the coefficients here. So B is 1. y naught is 0. So we get c is z0, c is -1, z0 is -2. 8 is not k because we need it in the form ax plus by plus cz plus k equals 0. And here the 8's on the right side, needs to be on the left. So you move it over and it'll be a -8. So like that. And then in the denominator, we need the a squared, b squared, c squared for the normal vector, which was 2 squared plus 1 squared plus 1 squared. So this is what we have to work out. So what do we have in the numerator? We're going to have absolute value of 0 plus 0 plus 2 minus 8. So -6. And then in the denominator, we got 4 plus 1 plus 1, which is 6. So it's 6 over square root 6. And you can simplify that and get square root 6. Okay. So we did it. So that's actually, what did we measure? This is the distance between the two planes that we were originally given. Okay. So I think I am done here. We are 1 hour and 46 minutes in. That seems plenty. All right, so I will talk to you guys next time for Monday's lecture, which hopefully will be shorter than this. See you guys then.